The last time we talked about the several convergence results for SGD. So for strongly convex functions, if we pick a diminishing step size, then this expected squared distance converge to 0 at a sublinear rate. And in particular, there are some results that shows that this is the optimal result. Like this is the algorithm that we can expect in this case. So informally, when minimizing strongly convex functions, no algorithm performing T queries to noisy first order oracles can achieve a better convergence rate. This means that if we consider minimizing a strongly convex function and consider a large class of algorithms, well, we can only access to T stochastic gradients in the first T iterations. Okay, no matter how you design this algorithm, but this is the boundary of this algorithm class. You can only have access to T stochastic or noisy first order gradient oracles. Among this class of algorithms, none of them can achieve a better convergence rate than 1/T. So this shows that the SGD algorithm with a diminishing step size is actually the optimal algorithm for minimizing strongly convex functions. And this convergence rate, 1/T convergence rate, is the optimal convergence rate. And more precisely, this is the statement of the result. Suppose we are dealing with such a class of optimization problems. Well, F is mu strongly convex, L smooth, okay, and the variance of the stochastic gradients are bounded. And this assumption we have mentioned in the last lecture. This is a standard assumption that we make in the analysis of SGD. Then the worst case iteration complexity for stochastic first order methods is given as follows. Basically, for any stochastic first order algorithms, we can construct a very hard problem specific to that algorithm. Okay? And these hard problems will make the algorithm has the following convergence lower bound. So this is to say that these stochastic first order algorithms cannot have a convergence rate better than this one. Like this is the best case that it can achieve. And we can see this complexity result. For the first term, it depends on the condition numbers, like square root of the condition number. And the inside we have log 1/epsilon. So the first term is basically dominated by this condition number. The second term, sigma square, is the noise variance of the stochastic gradient noise. So it's a sigma square divided by mu times epsilon. This epsilon is basically this is a 1/epsilon complexity. And in particular, if we do not have noise, consider the gradient descent case, sigma equals to 0, then the lower bound only contains the first term. And this is the convergence rate that we derived that is achieved by the Nesterov's accelerated gradient method. So we have talked about this before. But in the noisy case, when we talk about stochastic gradients, not full gradient, the lower bound has this additional term that involves the variance of the noise. So the noise will make the problem much harder, and then the convergence rate is limited to 1/epsilon in this case. for noisy case with large sigma, with large noise, the lower bound is dominated by roughly some constant times 1/epsilon, right? And this is basically is 1/epsilon is matches the convergence rate of this stochastic gradient descent. Right? So therefore, this shows that this SGD algorithm is optimal. It's actually optimal for minimizing strongly convex and smooth functions. And this is the comparison of the convergence rate and the complexities between gradient descent and the stochastic gradient descent. And we mentioned last time, gradient descent has converged for minimizing strongly convex function. Gradient descent converges linearly, very fast geometric convergence rate. So the iteration complexity is very small, but SGD converges sublinearly. So the iteration complexity is very high. Okay. However, the per iteration cost is a huge difference. For gradient descent, we need to compute the gradient for all the data samples. Suppose we have n data samples. Then we need to compute the gradient associated with all of them. We need to load the entire set of data. But for SGD, we just need, for every iteration, we just need to load a single data point, compute this gradient. So the total computation cost is n times log 1/epsilon versus 1/epsilon. So it depends on how big the data is and how accurate the target accuracy is. For many machine learning applications, well, we have big data, so this n is huge, and epsilon is not, it's relatively big, meaning that we are not looking for a very high accurate solution. So in this case, SGD is a very good algorithm for practical use in machine learning and the other signal processing areas. And then we talk about the convergence result of SGD for minimizing convex functions. And here the result is based on, in this case, the conclusion is that if we pick again a diminishing step size, but it decays slower, 1/√t. Pick this step size, then we have this convergence rate on the expected function value gap. This gap decays at the rate log t over √t. So it's roughly 1/√t because log is much smaller compared to square root. And here we need to consider this weighted average output. So the output is not the last iteration. It's actually a weighted average of all the iterations generated by this algorithm. And the weight coefficients are given by the step size used in that particular iteration. So it's a convex, this is like a convex combination. And then we talk about such a weighted average scheme can be very useful in practice. It can be used to reduce the variance of the iteration. So basically, the intuitions that doing such average, model average, or weight average, it can help mitigate the oscillation and reduce the variance in practice. And a very simplified scheme is basically consider the average of all the xi's generated by the algorithm. Well, all the weights are equal, simply 1 over t, where t is the iteration counter. And we can consider, here I give a very simple toy example to illustrate this idea. We can consider minimizing this simple quadratic function. Well, we know the minimizer is at 0. And this function is strongly convex. And it's also smooth. So it's a well-conditioned, very simple problem. And we consider implementing stochastic gradient descent with a constant step size. Okay, let's set the step size to be a constant eta. And then the stochastic gradient we use is the following one. If you take the gradient, it's just x, 1 over 2 square, x squared, taking the gradient is just x. So here we consider a noisy gradient. It's like the gradient plus a cassette t. This cassette t is a certain noise. And it satisfies some properties. Okay. So this is like a stochastic gradient that we consider. It is the gradient xt corrupted by a certain noise. And for this cassette t noise, it satisfies the following two statistical properties. The first one is conditional. It's like a zero mean, conditioned on all the noises in the previous iterations. This conditional expectation is 0. So the expectation of cassette t in the tth iteration is 0 given all the previous noises. And second of all, the covariance. The covariance of this noise is an identity. Again, conditioned on all the previous noises. This is the covariance because it is 0 mean. So this is the second moment subject 0. That's the definition of variance. So such a second order statistics equals to identity. It's an identity matrix. This means that if you write cassette t, to be a random vector, right? Because it's a vector added to xt, so it's supposed it has dimension d, and every coordinate is random, ct1 up to ct_d. Now, this expectation is the expectation of well, actually I should, okay, so this is a column vector. By default, these are all column. This is a column vector. So this is a column vector, ct, multiplied by the transpose, ct transpose, which is the row vector. Okay, so it's first is the product between column vector and the row vector, and then this gives a matrix. For this matrix, I take expectation, entry-wise expectation. So eventually it becomes the first entry is cassette1 t squared, right? And the C1t, C2t up to C1t, C dt, and so on. So you just, and then you take expectation for every entry. So basically, this is like a matrix where every entry measure the ij's entry measures the ith row j's column. This entry is the correlation between psi I t and the psi j t. So this and we are given that such a matrix is an identity matrix. Basically, we only have a diagonal term, and the diagonal term is just the variance of this each psi1, psi2, up to psi d. So, meaning that all these coordinates, all these random variables in all this noise in each coordinate, it has a unit variance, and moreover, they are pairwise uncorrelated, because because this is identity matrix, right? All these off diagonal entries, they are zero, and that simply means by definition they are pairwise uncorrelated. So basically, the first condition says that this noise vector has zero mean. This is easy to understand. And this condition, the second condition, says that okay, they are pairwise. Consider all the coordinates in this random vector. They are pairwise uncorrelated. But pick any pair, these two random variables are uncorrelated. And moreover, for each of them, they have a unit variance. And then we can, given these conditions, we can look at the SGD iterates. For example, x1 is x0 subtracts the gradient, stochastic gradient. Okay, and this is the stochastic gradient at iteration 0. This is the step size. And then rearranging the terms, it becomes 1 minus eta times x0 subtracts eta times psi0. And then we keep going. X2 equals to this is the update for x2. Okay, and then you plug in the expression of x1 obtained in the first row. So eventually x2 can be written as x0, psi0, and psi1. Okay, so you keep doing this. In the end, xt equals to this one. It's the initial point times 1 minus eta to the power of t. And then the rest are weighted. So like a weighted average of all the noises that we sampled in every iteration. Okay. So this will give us the position of xt. And we expect this xt to be will approach the minimizer 0. 0 is the minimizer of this problem. Okay. So so this is xt, and then we can consider the average of xt. We consider x bar t. X bar is the average. It's defined to be the average of this. Here is the average of all the xi's up to t. And then you basically take average on both sides over t. Okay, and then you can get this result. And this is an approximated result because the original expression can be highly complicated. But if you look at the first term is exactly the average of the first term here. Right. Here's t, and this is the average from k over k from 0 to t minus 1. And for the rest of the terms, again, it's like a t. For the rest of terms, this is an approximation. It is imprecise, but it is a very good approximation for large t. So and these terms is basically roughly equals to the average of all the noise multiplied by some constant coefficients. And moreover, the first term, right? We can calculate this this is like a summation of a geometric series. So we can calculate this exactly. And this exactly equals to this one. And as t goes to infinity, this will converge to 0. If t goes to infinity, this goes to 0. And this 1 over t goes to 0. So the entire first term converges to 0 as t goes to infinity. So, and moreover, for the second term, we can check that as t goes to infinity, the second term will roughly become the average of all the negative average of all the noise over all the noise terms. And from here you can see the advantage of using the weighted average. By averaging over xt, we end up with like an average of all the noise. And by law of large numbers, all these specific cases, they are zero mean and bounded second moment random variables. So by taking a sample average, this one will converge very quickly to 0. Okay, so this average will help to reduce the variance. And this, by the central limit theorem, this random variable, as t goes to infinity, it behaves like a Gaussian standard Gaussian random variable divided by square root of t. Okay. So you see the standards so this x bar t, okay, it will roughly be 1 over square root of t Gaussian. As Gaussian random zero mean standard covariance matrix, identity covariance matrix. The standard high dimensional Gaussian distribution weighted by 1 over square root of t, which means this is the Gaussian with zero mean and the covariance matrix. I think this should be T1 over 4 maybe. Because that's the this is sigma square, then then I think this should be T1 over 4. But anyway, this covariance term decays as t goes to infinity. Right? So this is like a zero mean Gaussian distribution, but the variance or the covariance will converge to 0. So it's a highly concentrated Gaussian. distribution. So in the end, once we do model average, once we average over the equations, this average will be very close to zero. The variance will be very, very small as t goes to infinity. So that's why in practice, we sometimes we usually do model average over this outputs generated sequence. This will help reduce the oscillations and makes the optimization smoother. And this is a more general quadratic problem. So it's we have A matrix A and B, and A is a positive definite matrix. And again, this is now the stochastic gradient is given by AX minus B. The gradient of this one, again, plus the same noise, zero mean noise with finite second order statistics. And the result says that considering like this is the average, model average, the difference between the model average and the minimizer at start. Such a random vector multiplied by square root of t. This entire thing converged in distribution to such a Gaussian distribution. The zero mean Gaussian with the covariance matrix given by A inverse times S times A inverse. Well, S is basically the second order, the covariance of this noise vectors. So this will converge in distribution to this Gaussian. And again, you can see that as t goes to infinity, I mean, you can divide both sides by square root of t. So intuitively, this one will be weighted by 1 over square root of t, and eventually the covariance will be very, very small. Okay? Will be decayed by this t. So asymptotically, the square, if we consider the square distance, then it is roughly 1 over t, right? If you square both sides, then we have square root of t becomes t, and you divide it, and you pull it to the right hand side. That is roughly 1 over t. This matches the convergence rate that we developed before. Yeah, but here our analysis is very tight in the sense that we directly look at the random behavior of the generated sequence. But in the previous analysis, we simply developed some upper bounds. And this is a proof sketch, but the idea is exactly the same. So you just expand the iterations, unroll the iterations over t one by one. So you have eventually you have this delta t bar is like the difference between your model average and the minimizer. This equals to such a complicated geometric summation. And so it's very complicated. And then the rest of the steps are simply using central limit theorems to consider the asymptotic behavior of these random variables. So we will not go into the details. And this can be this result can be further generalized to arbitrary strongly convex functions, not necessarily quadratic ones. So the story would be pretty much the same. Well, this is the gradient. abstract gradient of this objective function, like corrupted by a noise. So this is the stochastic gradient. And the conclusion would be the same, but those matrix A will be replaced by the inverse, like the Hessian matrix of this objective function at the minimizer point. Okay, so this is a generalized result. And then we can look at the homework. So last time we talked about part of this homework problem, like these three algorithms. And basically here we are implementing the standard SGD algorithm. Right? The first one is like every time we draw a mini batch of samples, either 16 or 32, you can define your own batch size. And the second one is to do model averaging. Once you generate that sequence of iterations, you at every time t, you consider the average of all the history xt's. And the third one is to further add a momentum to this algorithm. So you simply follow that accelerated gradient method, the momentum that we used in the accelerated gradient method, replacing the gradient by the stochastic gradient. And the first three algorithms are using sampling with replacement. That means every time you, in every iteration, once you draw that mini batch of data samples, you will put it back so that in the next iteration, you will again randomly pick another 16 or 32 samples from the entire data set. Okay, this is called sampling with replacement. Every time you put it back. So every time you draw a mini batch of samples from the same data set. But there's an issue with this sampling with replacement scheme. And we can illustrate this idea. Let's say you have 10 data points. Or maybe 5. Let's make it simpler. Let's say you have 5 data points. And this is your iteration. Okay. Let's say every time you pick 2, your batch size is 2. So every iteration you will draw 2 data samples out of this data set 5. Okay. So maybe the first iteration you pick the 1 and 4. That's your first mini batch. And then maybe the second iteration. Now after that, you will put it back. So in t equals to 1, again you will sample 2 points from this 5 points. Maybe you sample this 2, maybe t equals to 2, you do it again, you sample 4 and 5, and so on. Okay. So you can see that it is possible that a certain data sample will be visited more often than the other data samples. In this case, data point 4 is used 4 times, but 2 and 3, 1, 2, 3, 5, they are only used 1 time. So this is like this will create a larger variance in the training. This is like you are paying more attention to the data sample 4, but paying less attention to the other samples. And this will create a bias. Okay. Especially when your data set is not that big. So that's why here I mentioned the other sampling schemes, the sampling without replacement. Okay, and so the sampling without replacement is as follows. Say you have six data samples. We need an even number here. So what you do is that you first shuffle. You do a random shuffling. There are some built-in functions. Basically, you shuffle these six numbers or index, whatever. You do a random shuffling. Maybe it becomes 3, 1, 2, 4, 6, 5. You first do a random shuffling, and then you started to pick. Like you started to run your algorithm, and every time you pick two data samples, right? Let's assume your batch size is still 2. So you first do a random shuffling, and then in first iteration, you use first 2. Second iteration, you use the second mini batch. In the third iteration, you use 6 and 5. Okay, you do that. You pick them sequentially, and in a non-overlapping way. Okay, one by one or mini batch by mini batch. After these 3 iterations, you see you have passed over this data set for once. Like every single data point is used exactly once, right? So everybody is equal. Everybody's equal. And then after finishing this, after passing over the entire data set, you will reset. You reset. What you do, you do a random reshuffle. Okay, you reshuffle this index again. So this time it could be 6, 2, 4, 3, 1, 5. Okay, so you do another random reshuffle. And then you continue the fourth iteration. In the fourth iteration, you pick this 2, and then fifth iteration, you get this 2. In the sixth iteration, you get the last 2. Okay. And we call every random reshuffle an epoch. It's like a big period of shuffling. And you keep doing this again and again until you run the desired number of iterations. Okay, and you see that the nice thing about this sampling is like this is called sampling without replacement. Why? Because it feels like in the first iteration you sample 1 and 3, and then in the second iteration you will never use 1 and 3. You pick another 2 samples from the rest of the data points, so you get 2 and 4. And then in the third iteration, you will never use 1, 3, 2, 4. You will only use the rest of 2 data points, 6 and 5. So you never put them back, and then you keep. So this is called sampling without replacement. And in this scheme, every data point, first of all, still we are doing random sampling. There are some randomness, and moreover, every data point will be used exactly once in every epoch. Every data point used once. So this sampling will usually it provides a better performance because it will use every data point exactly once. So this will never happen, but a single data point may be sampled more frequently than the others. So in the homework, for the rest of the for the last three, for the next three implementations, we are doing still the same setup, but with sampling without replacement. Okay. So we are going to compare all these different settings. And you may observe a gap between these two sampling schemes. Usually the sampling without replacement will be faster, but sometimes they are very close to each other. It depends on your data. And the last one is gradient descent plus momentum. We have done this before. But again, in your plot, the y-axis is again the objective function value. This is the same. The x-axis is not the number of iterations. We talked about this last time. It is the number of data points that we have used. Okay. For gradient descent, in every iteration, you will sample all the data points, all the number of data points. And the second simulation is simpler. For S3D with sampling with replacement, try different batch size because here you are fixing a certain batch size. Okay, so in the simulation too, we will try different batch size and set the learning rate to be proportional to the batch size. So alpha times batch size. Well, alpha is some hyperparameter that you need to fine tune. Okay. The idea is that in practice, this is a very useful learning rate rule. Basically, it is proportional to a batch size. If you are using a large batch size, that means every time you are loading more data. Okay, and there's a trade-off here. If you use more data, the variance of your stochastic gradient will be smaller because you are closer to the full gradient. But on the other hand, you need to, it costs more computation resource because of this batch size. So once you use more data, if it's a larger batch size, meaning that you are using more data you are loading more data every time, then you can take a larger step. Intuitively, you can take a larger step. So the learning rate can be proportional to B. And the question is, you can plot the curves. Which batch size converges faster? Maybe the fastest. You will see a choice of the best batch size. It is neither too big nor too small. There's a sweet point here. Right. So in practice, we almost never use gradient descent to deal with large scale problems. We never use stochastic gradient descent with batch size 1. That is too inefficient. Right? If your data set has 1 million data samples, you need to run 1 million steps to pass over the data for once. It's not efficient. So there's always a good choice, a right choice of batch size for any specific problem. But the learning rate should be adjusted according to the batch size that we pick. So I think this is everything about the stochastic gradient. And next time we can, we still have several lectures, so we can spend more time on the last lecture, where we are going to talk about, this is a very long lecture, we have 50 slides. So we are going to talk about some variance reduction methods for stochastic gradient descent. And intuitively, if you implement the stochastic gradient descent, you will see that it has a lot of oscillations sometimes. So because the gradient is noisy and we are not expected to obtain a very smooth convergence curve. Yeah, that's why we want to do a model averaging. Let's go back to here. Yeah, we want to do a model averaging so that we can get this a reasonable convergence rate. But the question is, can we further improve this this result? If we go to the complexity, can we further improve these complexities? Like gradient descent is one extreme case where every time, well, we have a very fast convergence rate, but every time we pay a lot of cost just to deal with all the data in every iteration. SGD is another extreme case where every time we are dealing with a single data or small mini batch of data, but the convergence rate is very slow. Okay. So the question is, can we do something in between? Can we combine the advantage of both methods and really get the best complexity results? Okay. So we have shown that, like the previous discussion, these optimality results, these lower bounds, they are about iteration complexities, meaning that you can never beat these complexities. But for the computation cost, when we can further consider the factor of data size in this problem, the computation cost can be further improved between these two. So that is the motivation for the next lecture. We are going to introduce several interesting variance reduction techniques to accelerate the convergence of stochastic gradient descent and analyze their convergence. Okay, and I think these are the three: SVRG, Sarah, SDCA. But I think the first one is the most widely used one. Okay. So I think we can end early today, and we can spend more time on the simulations. If you have questions, I think at some point I will hold an office hour, and I can answer all the questions about the final project and homework 9. Okay, so enjoy the Thanksgiving, and I will see you guys next Tuesday.
Thank you.